Welcome to the next video in systems programming video series. In this, we're picking up where we left off in the previous video. And so moving on to this problem number 3, or part 3, I guess you could say, of question 2 from the JAM number 4. Here, we want to draw the contents of the register, and over here I have reproduced these values just for easy reference and comparison. Here I'm just going to leave these values, the initial values, unchanged, and then I'll just edit these as we do a bit of a walkthrough for the assembly instruction. So we want to draw the contents of the registers in stack after executing this particular instruction, which is at the instruction, what is it, the PID or whatever we call this here at this address, which if we come back up here to look at the assembly, is this line right here. So we want to say what the contents of all these values are after running this line of assembly. So we need to first process the first several lines of assembly. This would end BR64. I could go look up what that is, but I don't think we need to worry about that. The first thing to worry about is this push instruction. So we are going to start from the current value of the stack pointer, which is 0, and the RBP, the base pointer, which is also 0. And we are going to, do I have that right? Did I copy those values correctly? I did not, so I think I need to fix that. So EDX is correct, RBP is correct, the stack pointer is 048, and let's make that the same over here. And ESI, EDI, RIP. Okay, so now it's correct. So yes, I want to perform this call to push and push from the source the RBP values. A call to push will increment the stack pointer by 8. Let's come back over to here and just recall that this is what a push does. So we will subtract 8 from the stack pointer. So the new value of the stack pointer is going to be that, because we're subtracting 8 from the old value of the stack pointer. And then we are going to move the source data into the stack pointer effectively, or what is located at that stack pointer. So the important thing is just that the thing located at this address, which I don't think in this problem we are really meant to represent in any way, because we have this like memory address here, but that's not the one that we're talking about there, I don't think. Yeah, no, I don't think that is. So although we are going to move the value of RBP into this address, we're not going to represent that in any way. I don't think we're supposed to. So I think that's the push, right? I think we've now done everything that we need to do for the push, just remembering that the RBP value is located where the RSP address is pointing. Okay, the next thing to do is to move the RSP address into the RBP address. So that's going to show up here where RBP now stores the current value of RSP. So that is now going to become 40. What this effectively means or corresponds to is that we have pushed the base pointer onto the stack, and we've now made a new base pointer which is at the same place as the stack, so that we've effectively sort of initialized a new stack frame for the execution stack. They are now, right, like in a new stack frame, the base pointer and the stack pointer are pointing at the same place until the stack has some reason to grow. Finally, we are going to execute the line that was the whole point of this question, and that is to subtract 10, well, 10, 1, 0 in hex, that's 16, but in any case, you could almost imagine that it's 10. That's the subtraction from the stack pointer, and there it is. So there is the answer to this problem of drawing the contents of the registers and stack. Well, I guess I am drawing the contents of the registers. Yeah, if I were to draw the content of the stack, then I would maybe say that down at the very bottom is like the main stack, and as far as we know, there's no reason to think that there's anything in the main stack, so that would be at like stack level 0. But then there's this push, right, this call to push, so stack level 0 becomes 1, and we get a new stack level. And then at this new stack level 0, there is just the value of RBP that we just pushed. So that was the old value of RBP when the call to push occurred. And so OXO, that is pushed onto the stack. I hope the diagram makes sense. I'm just not bothering to get out drawing equipment to try to draw this by hand, but I think this hopefully makes sense. Okay, so let's move on to the next. So what is the memory, or what is the translation of the memory form? So what is that? And so here I am answering part 4. I guess this we could say it is answering part 3. But part 4, right, so what are we doing here? So we are going to take the address at RBP, whatever that is, right? I think in this part of the question, we're not necessarily meant to actually think about the specific values in the specific problem, but just more to answer this somewhat more abstractly. What is this supposed to mean in general? It should mean take the address %RB subtract 8. That's what this minus OX8 on the outside is meant to do, is to offset that address by 8. So in that case, subtracting 8, and then look up the memory at that resulting address. What is the SHL instruction? That is the shift left instruction. Okay, next, what are the contents of EAX? After executing this line, so let's go find that line ending in 15C. So here, okay. So I guess we just want to, as before, continue proceeding through the rest of this. As we said before, this goes from the base pointer, shifts the address by 8 upward, and then looks up the memory there. So we are going to move this value, which I think we already said in the previous video is equivalent to the number -9. So this is the number -9, and we're going to move it. And why move L? Move L is basically the same as move, but for a value that is restricted to 32 bits rather than move, which does a full 64-bit operation. This only requires 32 bits, and so we'll use the slightly more conservative move L command to move this number, -9, into this memory address. So that's going to affect the memory, and if we were to take this and subtract 8 from it and then look up the memory address there, we could work out what that is, but I'm not sure we need to because, again, I think that's not part of the information that we're tracking here. The only other piece of information that we're tracking other than these registers is this right here, which does not seem to correspond to the address that is saved by doing this. So in any case, when we do this instruction, where did it go there? When we do this instruction, we are moving 9 into this address in memory, but we don't need to represent that here, I don't think. But then we do need to know that, because then we are taking the thing stored at that address in memory and moving it into the EAX register so that the new value of EAX at that line is going to be this number. Well, I might as well just copy it from here. And so I think that answers the question. Yes, I think that answers the question, because the question was about this 15C line. Okay, what are the contents of EAX after 15F? So that would be this, and so we're going to shift left. Okay, and I guess so this is saying that we're going to shift left by 2 places the value that is in EAX. So I guess we should say any left shift, whether it's logical or arithmetic. And I think this one is logical, but a left shift, it shouldn't matter which one it is. So we're going to shift left twice, and in either version of shift, that just puts zeros there, and we will simply truncate the leftmost digits over there. Although I guess actually, come to think of it, here we're working in hex, and so maybe I do want to just double check. I actually think the shift here is bitwise, not like whole hex digits. So I should be careful about that. EAX, actually problem number 6, the answer was OX, but now moving on to 7. We want to do a bit shift by 2. I think we can recognize the fact that any F corresponds bitwise to just a sequence of all ones. So that would be 1, 2, 3, 4 ones for the first F, and then another 4 ones for each F after that. So that's 4 Fs, 5, 6, 7. And then the last one is the hex code, or we want the binary code for the number 7, because this is the 2 to the 0 place, 2 to the 1, 2 to the 2. So 2 to the 2 is 4, together with another 2 is 6, together with 1 is 7. So that's 7. Okay. And so if we bit shift this by 2, then basically all those ones are going to carry over. So it's still going to be 1, 1, 1, 1, 1, 1. So that's 4 times 5, 6, 7, 8, but the right 2 digits are going to become zeros because we're shifting everything to the left, and you always pre-append zeros when you do these left shifts. This 0 is going to trickle left by 2 places and land here. So I should come over here and edit that. So there's the result. And then if we want to put that in hex, then that would be F. Might even be nice to try to align these so that we can see it. And okay, so then the question is, what goes here? So that's 8 and 4 is 12, plus 1 is 13. Okay, now what is 13 in hex? There's A is 10, B is 11, C is 12, D is 13. So this should be D. And then this is 8 and 4 is so just one smaller, so C. Okay, and there's the hex code for what is in the contents of EAX. I should probably go ahead and update it here. So let's say that's, okay, so getting back to this. Okay, so for problem number 8, what are the contents of RSI? And so RSI is essentially the full version of ESI. So ESI is for 32 bits. RSI is the full 64-bit thing. And so we want to, anyway, look at the state of things after executing 16B. So where's 16? So that's down here. Now, how well can we get away with not tracing everything that's going on, but simply focusing on what is the content of ESI? We will take the current value of EAX, move it into the memory address of -4 RBP. Then we'll take exactly that value, move it into, so EDX now holds what EAX holds, which is this thing. So I might want to just go ahead and update EDX here. Then we want to take RBP -8, which I think we last saw holds the value -9, right? So RBP -8 holds -9. I don't think that changed at any point. I don't think this changed the content of RBP at -8, or well, -8 relative to RBP. I think this should still be the number -9. And so that we move into EAX at this point, and so we should go back to calling this that hex -9 in 2's complement. Then we take that value and move it into ESI, so that should also be this. So there's my answer. Hope I got that right. My main concern is, does writing over -4 RBP actually write over -8 RBP? How many bytes are there? Of course, 4, right? So I am writing into 4 bytes. And if there's any spillover, right, if the amount of stuff here is bigger than that space of 4, then that would cause a problem. But this is EAX, not RAX. So it is only 32 bits, which is 4 bytes. So it seems to fit nicely in here and should not affect the memory that is located at this address. And so I think I'm right about that. And so what is in ESI? It is this X 1, 2, 3, 4, 5, 6, 7, and then a 7. So that's my answer to 8. And we'll end on 9. What are the contents of R after 16D? And so since we just said what are we doing? We're loading a value into, because that's a LEA, load effective address. So we are going to take the instruction pointer But I guess at this point, RAP should just be this right here. We would increase that by this E90 value. So we take this plus E90, and we would put that into RDI. So I think maybe here they have helpfully calculated this comment here, I think is a calculation of what, oh, actually, would this be where the memory comes in? So if we took, yeah, I think that's what's going on here. So if we took this value, added this hex number to it, I believe what it's telling us is that the result is this, because that's load effective address, not actually moving the memory content. So in fact, where did that go? So the answer to problem 9 would then just be the result of loading the effective address, and so that would just be that value. Here, let me just go copy it. Yeah, this thing. So it would effectively just be taking this and putting it into, where did it go? ESI, so this thing right here. So that's the value of ESI, that's what goes here. There's the difference between RDI and EDI. Well, this is RDI. What's the contents of RDI? That's that. All right, a long enough video. We'll finish off the rest in the next video.